Jupiter, the largest and most massive planet in the solar system, holds a prominent place in our understanding of the cosmos. Its sheer size and power dwarf the other planets, and its dynamic atmosphere offers a glimpse into the extreme forces that shaped our solar system. The study of Jupiter is not merely an exploration of a distant world. It is a journey into the heart of planetary science that provides insights into the origins and evolution of our cosmic neighborhood. Jupiter's atmosphere is a roiling, turbulent mass, primarily composed of hydrogen and helium, much like the Sun. However, what distinguishes Jupiter is the staggering variety of atmospheric phenomena. The most iconic of these is the Great Red Spot, a colossal storm that has raged for centuries. This massive anticyclone, large enough to engulf 2 Earths, is one of the most enduring weather systems ever observed. Its persistence and scale challenge our understanding of atmospheric dynamics and offer a window into the complex interactions between Jupiter's atmosphere and its powerful magnetic field. Beneath the seemingly endless clouds lies a mystery. Jupiter has no solid surface. Its gaseous layers blend into increasingly dense fluids as one descends, eventually leading to a strange, exotic form of metallic hydrogen which may generate its magnetic field. The planet's deep cloud belts and zones are fascinating in their own right, swirling with ammonia crystals and complex compounds, adding vibrant hues of white, brown, and orange to the planet's canvas. These bands are driven by jet streams much stronger than anything on Earth, contributing to the overall chaotic beauty of the gas giant. Jupiter is more than just its atmosphere. It is a planet surrounded by a complex system of rings and moons. Though its rings are faint and pale in comparison to the brilliant bands of Saturn, they speak of a violent history involving collisions and the gradual accumulation of material from various sources. However, it is Jupiter's moons that steal the show, a miniature solar system of their own. Each of the Galilean moons, Io, Europa, Ganymede, and Callisto, presents its own set of mysteries. Io, the most volcanically active body in the solar system, astonishes with its constant eruptions of sulfur and other materials, reshaping its surface on a geological timescale. Europa, with its icy shell and the possibility of a subsurface ocean, has become one of the most tantalizing candidates for the search for extraterrestrial life. Ganymede, the largest moon in the solar system, is unique in that it possesses a magnetic field and may also harbor an ocean beneath its icy crust. Meanwhile, Callisto, ancient and heavily cratered, offers clues about the early history of the solar system and also hints at the possibility of an underground ocean. Jupiter's magnetosphere is equally awe-inspiring. Stretching millions of kilometers, it encompasses a region far larger than the planet itself, trapping particles and creating radiation belts that dwarf Earth's Van Allen belts. This magnetic environment protects its moons from solar radiation, while also giving rise to spectacular auroras far brighter than those seen on Earth, as charged particles interact with the planet's atmosphere. Jupiter also plays a critical role in shaping the broader solar system. Its immense gravitational pull acts as a cosmic vacuum cleaner, diverting or capturing comets and asteroids that might otherwise pose a threat to Earth. This protective role may have been pivotal in preserving the delicate balance necessary for life to evolve on our planet. In this sense, Jupiter is not only a distant giant but also a guardian, shielding the inner planets from the chaotic dangers of space. From the early telescopic observations of Galileo to modern space missions like Juno and JUICE, our exploration of Jupiter has transformed our understanding of planetary science. Each new mission uncovers layers of complexity and mystery, from the dynamic storms that sweep across its surface to the icy oceans that may harbor life on its moons. Jupiter, in many ways, is a cosmic laboratory, a natural experiment in the mechanics of planetary formation and evolution. And as we continue to study this gas giant, we are not only learning about Jupiter but about the potential for life, the forces that shape worlds and the future of our exploration of the cosmos. Beyond its majestic atmosphere, moons, and magnetic field, Jupiter holds a key to understanding the early stages of planetary formation in our solar system. As the largest planet by far, Jupiter formed relatively quickly after the Sun, drawing in vast amounts of gas and debris left over from the solar nebula. Its massive gravitational influence helped shape the orbits of other planets, and it may have even played a role in preventing the formation of a planet in the asteroid belt between Mars and Jupiter. Instead, we find a region filled with remnants of rocky material, suggesting that Jupiter's early presence influenced the way the inner solar system developed. Scientists believe that by studying Jupiter, we can also better understand the formation of other gas giants both within our own system and beyond. In recent decades, the discovery of exoplanets, planets orbiting stars outside our solar system, has revealed that gas giants like Jupiter are relatively common throughout the galaxy. However, many of these exoplanets, known as hot Jupiters, orbit much closer to their parent stars than Jupiter does to the Sun, challenging previous models of planetary formation. The comparative study of Jupiter alongside these distant worlds offers valuable clues to understanding the diversity of planetary systems in the universe. One of the most captivating aspects of Jupiter's system is the potential for life beyond Earth, particularly on its moons. Europa, in particular, has garnered significant attention due to its smooth, icy surface and the strong evidence of the subsurface ocean beneath. The heat generated by tidal forces as Europa orbits Jupiter may keep this ocean in a liquid state, creating an environment where microbial life could potentially thrive. NASA's upcoming Europa Clipper mission aims to explore this moon in greater detail, searching for signs of life by analyzing the composition of the ice and investigating the plumes of water vapor that may erupt from its surface. Ganymede 2 presents an intriguing case for further study. As the largest moon in the solar system, Ganymede's magnetic field and subsurface ocean make it a potential candidate for harboring life, though less likely than Europa. Meanwhile, Callisto, once thought to be a geologically dead world, may hold surprises of its own, with recent evidence hinting at the possibility of a deep ocean hidden beneath its heavily cratered surface. These moons challenge our understanding of where life might exist in the universe, pushing the boundaries of astrobiology beyond the traditional focus on Earth-like planets. The exploration of Jupiter and its moons is not merely a quest for scientific knowledge, it is a profound search for our place in the cosmos. The possibility that life could exist in the dark, icy oceans of Europa or the volcanic landscapes of Io forces us to reconsider the conditions required for life. If life exists elsewhere in our solar system, even in microbial form, it would have profound implications for the likelihood of life elsewhere in the universe. Moreover, the study of Jupiter's extreme environments helps us understand the limits of life on Earth. From the deep-sea hydrothermal vents to the icy Antarctic lakes, Earth is full of extreme environments where life not only survives but thrives. These Earth analogues provide vital clues for scientists as they consider how life might adapt to the conditions on moons like Europa or Ganymede. The exploration of these distant worlds allows us to draw comparisons, helping to refine our understanding of the potential habitability of planets and moons elsewhere in the galaxy. The study of Jupiter is also a humbling reminder of the sheer scale of the universe. Its vast size and complex systems remind us of how small and fragile our own planet is by comparison. As we send probes and missions to study this gas giant, we are reminded of the challenges and rewards of exploration. In the face of such immense distances and extreme environments, each new discovery brings us closer to answering some of the most fundamental questions about the nature of the universe and our place within it. Jupiter is not just a gas giant, it is a window into the past, present, and future of planetary science. Its storms, moons, and magnetic field offer clues to the formation of planets, the potential for life beyond Earth, and the forces that shape planetary systems. As we continue to explore this majestic world, we uncover new mysteries and deepen our understanding of the cosmos. Each mission, each observation, and each new discovery pushes the boundaries of human knowledge, expanding our sense of wonder and our curiosity about the universe. In the end, the study of Jupiter is more than just a scientific endeavor. It is a journey of discovery, one that invites us to look beyond our own world and to consider the vastness of the universe. It challenges us to think about what it means to be alive in such a vast and complex cosmos, and to ponder the possibilities of life elsewhere. Jupiter, with all its mysteries and marvels, serves as a reminder of the infinite potential for discovery in the universe and the endless questions that await answers as we continue our exploration of the stars. As our understanding of Jupiter deepens, so does our appreciation for its complexity and its role in shaping not only the solar system but also our broader comprehension of planetary formation and the potential for life in the cosmos. The continuing study of Jupiter, both through telescopic observation and space exploration, is vital to answering some of the most profound questions humanity has ever asked. How did the planets form? Are we alone in the universe? What role do massive planets like Jupiter play in the development of habitable environments? One of the most striking features of Jupiter is its gravitational influence. It is often called the protector of the inner planets, including Earth, because its immense gravitational pull can act as a shield, deflecting or capturing many of the comets and asteroids that might otherwise impact the inner planets. However, it is a double-edged sword. While Jupiter can prevent catastrophic impacts on Earth, its gravity has also been responsible for diverting some objects toward the inner solar system, including those responsible for past mass extinction events on Earth. Yet, Jupiter's influence is not limited to destructive potential. Its role in the development of planetary systems may be far more fundamental. Scientists theorize that without Jupiter, the early solar system might have evolved very differently. A planet's enormous mass likely played a critical role in shaping the orbits of other planets, and may have prevented the formation of additional planets by clearing out debris and guiding material into stable orbits. In this way, Jupiter can be seen as a cosmic architect, shaping the layout of our planetary neighborhood. This idea extends to the broader search for exoplanets as well. In many star systems, massive planets like Jupiter are found close to their parent stars, defying previous expectations based on our solar system structure. These hot Jupiters may have migrated inward after forming further out, affecting the development of other planets in their systems. By studying Jupiter's long-term stability and how it has influenced the evolution of its moons and the other planets, scientists gain crucial insights into how planetary systems form and evolve, both in our solar system and beyond. Jupiter's own moons offer a diverse array of environments that push the boundaries of what we understand about habitability. The icy moons, particularly Europa, are key targets in the search for extraterrestrial life. Beneath Europa's frozen crust, scientists believe a vast ocean exists, kept liquid by the tidal forces generated as Europa orbits Jupiter. These same forces create friction and heat, which may produce hydrothermal vents on the ocean floor, similar to those on Earth, where life thrives in the absence of sunlight. The possibility that life could exist in such an extreme environment raises profound questions about where life might be found in the universe. NASA's upcoming Europa Clipper mission will investigate this moon in unprecedented detail. The spacecraft will map the surface, study the composition of the ice, and look for evidence of subsurface water and potential biosignatures. If life is found on Europa, it would not only be one of the greatest discoveries in human history, but would also fundamentally alter our understanding of biology and the conditions required for life. Meanwhile, missions like the Juno spacecraft, which has been studying Jupiter since 2016, continue to provide extraordinary insights into the planet's atmosphere, magnetic field, and interior structure. Juno has given scientists a new understanding of the Great Red Spot, revealing that the storm extends deep into the planet's atmosphere, far beyond previous estimates. It has also captured stunning images of Jupiter's cloud tops, showing intricate patterns of swirling storms and vortices that offer clues about the planet's weather systems. One of the surprising discoveries from Juno has been the complexity of Jupiter's magnetic field. Unlike Earth's relatively stable dipole magnetic field, Jupiter's is highly irregular, with strange patches of strong and weak magnetic forces. Understanding how this magnetic field is generated and how it interacts with the planet's atmosphere and surrounding space environment is crucial, not only for studying Jupiter itself, but also for understanding magnetic fields on other planets and even exoplanets. Looking ahead, the European Space Agency's JUICE mission Jupiter Icy Moons Explorer, set to launch in the 2030s, will continue to expand our knowledge of Jupiter and its moons, particularly Ganymede, Callisto, and Europa. This mission aims to explore the habitability of these moons and investigate the conditions that could support life in the icy environments of the outer solar system. As the exploration of Jupiter and its moons progresses, so too does our understanding of the solar system's history and the dynamics that govern planetary systems across the galaxy. Jupiter is not only a focal point of scientific inquiry, but also a symbol of the power and beauty of the universe. Its swirling clouds, towering storms, and distant moons remind us of the vastness of space and the endless possibilities it holds. But beyond the scientific and exploratory significance, the study of Jupiter touches on deeper, philosophical questions about humanity's place in the cosmos. As we send probes to distant planets and peer through telescopes to observe worlds light years away, we are driven by the same curiosity that has fueled exploration since the dawn of human history. The more we learn about Jupiter, the more we realize that our understanding of the universe is still in its infancy, with each new discovery revealing more mysteries to be unraveled. In the end, the study of Jupiter is a journey not just into the heart of the gas giant, but into the nature of the universe itself. It challenges our preconceptions about what planets are and what they can become, pushes the boundaries of astrobiology, and deepens our understanding of how planetary systems form and evolve. Jupiter's mysteries, once confined to the realm of ancient mythology, are now the subject of cutting-edge science, reminding us that exploration is not just about seeking new worlds, but about expanding the horizons of human knowledge. Jupiter's story and our ongoing efforts to understand it are a testament to the enduring human drive to explore the unknown, to ask questions, and to seek out the deeper truths of the cosmos. Jupiter, in all its grandeur and complexity, represents a frontier of discovery that continues to inspire scientists and explorers alike. Its vast storms, intricate atmospheric layers, and enigmatic moons compel us to probe deeper into the forces that govern not just Jupiter, but planetary systems throughout the cosmos. As we unravel Jupiter's mysteries, we are also piecing together the larger puzzle of how planets form, evolve, and interact within their solar systems. One of the most profound aspects of Jupiter's study is its connection to the early days of the solar system. Jupiter likely formed within the first few million years after the Sun ignited, gathering much of the gas and dust left over from the formation of our star. Its sheer size allowed it to dominate its region of space, and it likely influenced the formation and migration of the other planets. In fact, many astronomers believe that without Jupiter's stabilizing presence, the inner solar system, including Earth, might have experienced far more frequent bombardments from comets and asteroids, potentially making the emergence of life on our planet more difficult. Jupiter's role as a gravitational giant, shaping the paths of smaller objects and protecting the inner planets, also links it to the broader cosmic story of planetary systems. In recent years, astronomers had discovered thousands of exoplanets, planets that orbit stars beyond our Sun. Many of these are gas giants like Jupiter, and their study has provided new insights into the diversity of planetary systems. In some systems, gas giants are found orbiting extremely close to their stars, defying the expectations set by our own solar system. These hot Jupiters, as they are called, challenge our models of planetary formation and migration, suggesting that gas giants can move dramatically over time, influencing the structure of their systems in ways we are only beginning to understand. Jupiter's exploration through missions like Nota and future missions like Justet not only enhances our understanding of this colossal planet, but also informs our study of gas giants across the galaxy. The comparison between Jupiter and exoplanets can help answer fundamental questions about how planets form, why they migrate, and what conditions might be necessary for the development of habitable environments. By studying Jupiter, we are essentially building a foundation of knowledge that applies to planetary science on a universal scale. Perhaps one of the most intriguing aspects of Jupiter's system is its potential for harboring life, not on the planet itself, which is inhospitable due to its extreme conditions, but on its moons. Europa, with its thick, icy shell and strong evidence of a subsurface ocean, remains one of the most promising places in the solar system to search for extraterrestrial life. The potential for hydrothermal activity on Europa's ocean floor, similar to the deep-sea vents on Earth where life thrives in the absence of sunlight, has sparked the imaginations of astrobiologists. If microbial life exists on Europa, it would be a transformative discovery, reshaping our understanding of life's potential to exist in environments vastly different from Earth's. The search for life on Europa is part of a broader scientific mission that spans beyond just one moon or planet. It's a search for a deeper understanding of the conditions that give rise to life. By exploring the icy oceans of Europa, the volcanic landscapes of Io, and the magnetic environment of Ganymede, scientists are not just looking for life, but are also probing the limits of what we consider habitable. These moons are laboratories that allow us to test theories about life's resilience and adaptability. Jupiter's magnetosphere, too, adds another layer to the planet's complexity. It is the largest and most powerful magnetic field of any planet in the solar system, stretching millions of kilometers into space. This vast magnetosphere traps charged particles, creating intense radiation belts that would be lethal to humans but also generate some of the most spectacular auroras ever seen. These auroras, far brighter than those on Earth, are caused by the interaction between Jupiter's magnetic field and the solar wind, offering scientists a natural laboratory for studying magnetic fields and their effects on planetary atmospheres. The deeper we look into Jupiter's magnetosphere, the more we learn about magnetic fields across the universe. Understanding how Jupiter's field is generated and maintained helps inform our models of magnetic fields on Earth and other planets, including exoplanets. It also provides clues about how such fields protect atmospheres from solar radiation, a key factor in determining a planet's ability to support life. Jupiter's magnetic field is so powerful that it even affects its moons, particularly Io. Io's volcanic activity is driven in part by the gravitational and magnetic forces exerted by Jupiter. The Moon's constant volcanic eruptions release enormous amounts of sulfur into space, which in turn interact with Jupiter's magnetosphere, creating massive radiation belts around the planet. This dynamic relationship between Jupiter and its moons offers a unique insight into how gravitational and magnetic forces can shape entire planetary systems. As we continue to study Jupiter, we are constantly reminded of the intricate web of interactions that define planetary systems. Jupiter's moons, its rings, its atmosphere, and its magnetic field are all part of a larger system of forces that have evolved over billions of years. Each new discovery about Jupiter adds a piece to the puzzle, helping us understand not only this giant planet but also the broader dynamics that govern planets throughout the galaxy. The future of Jupiter exploration holds even more promise. As technology advances, our ability to send more sophisticated probes and spacecraft to Jupiter and its moons will enable us to explore these worlds in greater detail. Missions like Start will focus on Ganymede, Callisto, and Europa, investigating their potential for supporting life and their role in the evolution of the solar system. With each new mission, we come closer to answering the age-old questions about the origins of life, the formation of planets, and the nature of the universe itself. Jupiter stands as a testament to the power of exploration and the boundless curiosity that drives humanity to reach beyond our own world. In studying this gas giant, we are not just learning about a distant planet, we are exploring the fundamental forces that shape the cosmos and our place within it. As we peer into the depths of Jupiter's atmosphere, traverse the icy landscapes of its moons, and map the contours of its magnetic field, we are reminded of the vastness of the universe and the infinite potential for discovery that awaits us among the stars. The allure of Jupiter extends far beyond its colossal size and dynamic system of moons, atmospheres, and magnetic fields. In many ways, the gas giant encapsulates some of the most fundamental questions in astronomy, planetary science, and the search for extraterrestrial life. Each layer of exploration, whether it's through close-up missions or powerful telescopic observations, deepens our understanding of not only Jupiter itself, but also the larger forces that have shaped the cosmos. One of the fascinating areas of study related to Jupiter is the planet's internal structure. While we know that Jupiter lacks a solid surface, the composition of its interior remains an area of ongoing research. Beneath its thick, swirling clouds lies a realm of immense pressure and extreme temperatures. As one descends deeper into the planet, hydrogen gas is compressed into a strange metallic form that conducts electricity, possibly generating the planet's intense magnetic field. At the core, scientists hypothesize that a rocky or icy center may exist, though its exact nature is still a mystery. Understanding Jupiter's interior has broader implications for the study of gas giants beyond our solar system. By modeling the planet's internal structure, researchers can make comparisons with exoplanets, many of which are similar in size and composition to Jupiter. Such studies can help refine our theories of how gas giants form and evolve, particularly in environments that differ from our own solar system. Moreover, the investigation into the physics of metallic hydrogen, a material likely common in many gas giants, offers insights into planetary magnetism and other extreme states of matter that are not yet fully understood. Jupiter's vast system of moons also continues to captivate scientists. Beyond the Galilean moons, Jupiter has dozens of smaller moons, each of which plays a role in the dynamic environment surrounding the planet. These moons range from irregularly shaped captured asteroids to more geologically active worlds. The sheer number of moons orbiting Jupiter presents an excellent opportunity for studying the interactions between moons and their parent planet in a complex gravitational system. For example, the volcanic moon Io, with its intense geological activity, is constantly reshaped by the tidal forces exerted by Jupiter's gravity. This constant gravitational tug generates immense heat within Io, driving volcanic activity on a scale unmatched anywhere else in the solar system. Io's eruptions are so powerful that they can be seen from space. With plumes of sulfur and other materials shooting hundreds of kilometers into the sky, these volcanic outbursts contribute to the intricate relationship between Jupiter and its magnetosphere, as Io's ejected materials help fuel the radiation belt surrounding the planet. Europa, in contrast, presents a more subdued but equally fascinating environment. Icy surface is riddled with cracks and ridges, evidence of the powerful tidal forces that deform the moon as it orbits Jupiter. Beneath this icy crust, scientists believe there exists a global ocean of liquid water, kept warm by the same tidal forces that drive Io's volcanism. The discovery of water plumes erupting from Europa's surface further supports the idea that its subsurface ocean is in contact with the Moon's rocky mantle, potentially creating conditions similar to those at hydrothermal vents on Earth's ocean floor, places where life thrives in the absence of sunlight. The presence of water and the potential for chemical reactions beneath Europa's ice make it one of the most compelling targets in the search for life beyond Earth. Future missions, such as NASA's Europa Clipper, will investigate this possibility by flying close to Europa, capturing high-resolution images, analyzing its surface composition, and probing for signs of habitability. If Europa's ocean contains the right ingredients for life, it could provide a glimpse into what life might look like in environments radically different from our own. Ganymede, the largest moon in the solar system, is another focus of exploration. Ganymede is unique in that it has its own magnetic field, an unusual trait for a moon. This magnetic field, along with its suspected subsurface ocean, makes Ganymede a prime candidate for studying the conditions necessary for habitability. While Ganymede's surface is a mix of icy plains and ancient cratered regions, it may harbor a more dynamic and active interior than previously thought. Callisto, the most heavily cratered of Jupiter's major moons, represents a snapshot of the early solar system. Unlike its sibling moons, Callisto shows little evidence of geological activity, and its heavily cratered surface has remained largely unchanged for billions of years. This ancient landscape offers scientists a window into the past, preserving a record of the solar system's early history. Callisto also presents intriguing possibilities as a base for future human exploration due to its relatively low levels of radiation compared to other moons in the Jovian system. As we continue to study Jupiter and its moons, we are also drawn to the planet's rings, an often overlooked aspect of its system. While Jupiter's rings are not as prominent as Saturn's, they provide valuable clues about the planet's past. These faint rings are composed mostly of dust and small particles, likely originating from collisions between Jupiter's moons and passing asteroids or comets. The study of these rings can help scientists understand the dynamics of debris in the solar system, as well as the forces that shape ring systems around giant planets. Jupiter's influence extends far beyond its immediate surroundings. Its gravitational field affects not only its moons, but also the entire solar system. For example, Jupiter is responsible for the existence of the asteroid belt, a region between Mars and Jupiter filled with rocky debris that never coalesced into a planet due to the gas giant's immense gravitational pull. Jupiter's gravity also plays a key role in guiding comets into orbits that bring them close to the Sun, including many that have been observed from Earth. Throughout human history, Jupiter has been a symbol of mystery and power. From ancient myths that associated it with gods and kings to the groundbreaking observations of Galileo Galilei, who first saw its moons, Jupiter has always captured the human imagination. Today, as our spacecraft venture deeper into the outer solar system, Jupiter continues to inspire awe and curiosity. It serves as both a natural laboratory for studying planetary systems and a reminder of the vast and dynamic nature of the cosmos. The study of Jupiter is, in many ways, a testament to humanity's insatiable curiosity. With each new discovery, we push the boundaries of our knowledge, revealing the complexity of our solar system and opening doors to the study of distant worlds. As we continue to explore Jupiter, we move closer to understanding the fundamental processes that govern the universe, from planetary formation to the potential for life beyond Earth. In this sense, Jupiter is not just a planet. It is a gateway to deeper cosmic truths, inviting us to explore, to question, and to wonder at the vastness of the universe. It stands as a beacon for future exploration, a reminder that the answers to some of the most profound questions about existence may lie within the swirling clouds of this gas giant or beneath the icy crust of one of its moons. And as we look to the future, the study of Jupiter promises to unlock even more mysteries, each discovery bringing us closer to understanding our place in the universe. The exploration of Jupiter and its vast system represents not just the pursuit of knowledge about a single planet, but a deeper understanding of how the solar system functions as a whole. As we continue to unravel Jupiter's mysteries, we find that the planet serves as a lens through which we can view the broader dynamics of planetary science, astrobiology, and even cosmology. One of the remarkable features of Jupiter is the sheer scale of the forces at work within and around it. Its magnetic field is the strongest of any planet in the solar system, stretching far beyond the planet itself and interacting with both its moons and the solar wind. This magnetosphere, a complex structure filled with charged particles, creates some of the most dramatic phenomena in the solar system, including intense auroras near Jupiter's poles. These auroras are not only visually stunning but also scientifically significant, offering insight into how magnetic fields and charged particles interact, a process that occurs throughout the universe on various scales. The ongoing Juno mission has revolutionized our understanding of Jupiter's magnetic field. Juno's detailed measurements have revealed that the field is far more irregular than previously thought, with unexpected concentrations of magnetic flux in certain regions. These findings have challenged existing models of how Jupiter's magnetic field is generated, suggesting that the planet's internal dynamics are far more complex than anticipated. Understanding Jupiter's magnetosphere is crucial not only for planetary science, but also for astrophysics, as magnetic fields are key to understanding many processes in the universe, from star formation to the behavior of distant exoplanets. Beneath Jupiter's atmosphere lies another enduring mystery, the possibility of a solid core. For decades, scientists have debated whether Jupiter has a solid or semi-solid core, or if its internal structure is composed primarily of gas and liquid without a definitive boundary. Juno has provided new data suggesting that Jupiter's core may be fuzzy, a diffuse region of heavy elements mixed with lighter gases like hydrogen and helium. This could indicate that Jupiter's core was disrupted early in its formation, possibly by a massive collision with another protoplanet. Such a scenario would help explain Jupiter's current structure and offer clues to the chaotic environment of the early solar system. The concept of planetary collisions as a formative process extends beyond Jupiter and helps explain many features of planetary systems, including our own. Earth's moon, for example, is thought to have formed from debris left over after a Mars-sized body collided with the young Earth. By studying Jupiter and considering the role of impacts in shaping its interior, scientists gain valuable insights into the violent processes that shape not just our solar system, but planetary systems throughout the galaxy. While Jupiter itself is unlikely to harbor life due to its extreme conditions, its moons remain some of the most promising locations for finding extraterrestrial life within our solar system. Europa, with its subsurface ocean, remains the focus of intense interest. Scientists have long speculated that if microbial life exists anywhere beyond Earth, Europa is one of the most likely candidates. The potential discovery of life in Europa's ocean would have profound implications for our understanding of biology, evolution, and the conditions necessary for life to emerge. The upcoming Europa Clipper mission aims to answer some of these questions by closely studying the Moon's icy surface and probing its subsurface ocean. This mission will analyze the chemical composition of Europa's surface, investigate the structure of its ice shell, and search for signs of life or prebiotic conditions. If life exists on Europa, it would likely be in microbial form, adapted to survive in extreme environments similar to Earth's deep ocean hydrothermal vents. The discovery of life in such an environment would not only confirm that life can exist in places other than Earth, but also expand our understanding of where life might thrive in the universe. Ganymede and Callisto, though less frequently discussed in the search for life, also offer tantalizing possibilities. Ganymede's magnetic field and potential subsurface ocean make it an interesting target for further exploration, while Callisto's ancient surface, relatively unchanged over billions of years, preserves a record of the solar system's early history. Each of these moons, with their unique environments and characteristics, contributes to the larger narrative of Jupiter's system as a diverse and dynamic region ripe for exploration and discovery. Beyond its moons, Jupiter's own environment poses intriguing challenges for future human exploration. While the intense radiation and crushing atmospheric pressure make landing on Jupiter impossible, the planet's moons, particularly Callisto, have been considered potential bases for human missions. Callisto's relative distance from Jupiter's radiation belts and its stable surface make it a candidate for future exploration, perhaps even as a way station for missions deeper into the outer solar system. NASA has considered the possibility of establishing a base on Callisto as part of a long-term strategy for human exploration of the outer planets. Such a base could serve as a hub for studying not only Jupiter and its moons, but also as a staging ground for missions to Saturn or beyond. Jupiter's importance to the broader dynamics of the solar system cannot be overstated. Its massive gravity has acted as a stabilizing force, shepherding asteroids and comets and preventing more frequent collisions with Earth and other planets. However, Jupiter's gravitational influence has also been a double-edged sword, responsible for sending some comets and asteroids on collision courses with the inner planets. These dual roles, as protector and potential threat, highlight Jupiter's complex relationship with the rest of the solar system. Looking further ahead, the study of Jupiter holds implications for our understanding of planetary systems beyond our own. Many of the exoplanets discovered in recent years are gas giants similar to Jupiter, and by studying Jupiter in detail, scientists can apply this knowledge to understand the behavior of distant planetary systems. The discovery of hot Jupiters, gas giants that orbit very close to their parent stars, has challenged previous models of planetary formation and migration. Jupiter's relatively stable orbit far from the Sun contrasts with the more volatile behavior of these distant gas giants, raising questions about how and why planetary systems evolve differently. As we continue to explore Jupiter, both through robotic missions and telescopic observations, we are reminded that the planet is not just a distant world, but a crucial piece of the cosmic puzzle. Its dynamic atmosphere, powerful magnetosphere, diverse moons, and influence on the solar system make it a focal point for understanding how planets form, evolve, and interact with their environments. Each new discovery about Jupiter brings us closer to answering the fundamental questions about our origins, the nature of life, and the future of space exploration. In the grand scheme of the cosmos, Jupiter is a reminder of the vast and complex forces at play in the universe. It stands as both a symbol of the beauty and mystery of the solar system and a gateway to understanding the broader mechanics of planetary science. As we gaze up at the giant planet, with its swirling clouds and distant moons, we are reminded of our own small place in the universe, and the limitless possibilities that await us as we continue to explore the stars. Jupiter remains a boundless source of fascination, and its continued exploration opens new doors to understanding not only the planet itself, but the deeper mechanisms of our solar system and the universe at large. Its massive size, dynamic systems, and gravitational dominance give it a crucial role in shaping the environment around it. As we continue to delve into its mysteries, each discovery enhances our comprehension of planetary formation, the potential for life beyond Earth, and the complex dynamics that govern cosmic systems. One of the most captivating aspects of Jupiter is how it helps us study the broader phenomenon of gas giants and other star systems. With the explosion of exoplanet discoveries, astronomers have found numerous Jupiters orbiting stars at various distances. By studying our own Jupiter up close, we can draw parallels with these distant worlds, refining our models for gas giant formation and migration. For instance, many exoplanets identified as hot Jupiters orbit surprisingly close to their stars, suggesting they may have formed farther out and migrated inward over time, a process that Jupiter seems to have avoided. Understanding why Jupiter stayed in a relatively stable orbit, while other gas giants elsewhere didn't, adds another layer to our understanding of planetary system diversity. This study also extends to questions of habitability. In systems with massive gas giants like Jupiter, the presence of such planets can either create or destroy opportunities for life on smaller, rocky planets nearby. Jupiter's gravitational influence, for instance, has deflected many potentially hazardous comets and asteroids from crashing into Earth. On the other hand, its powerful gravity has also sent objects from the distant reaches of the solar system hurtling toward the inner planets, as was the case with the comet Shoemaker-Levy 9, which spectacularly collided with Jupiter in 1994. This dual role, as both a protector and a disruptor, mirrors the delicate balance required for life to evolve in any planetary system. Jupiter's moons continue to play an essential role in this story. The ongoing search for life on its icy satellites, particularly Europa, Ganymede, and Callisto, pushes the boundaries of our understanding of biology. Europa, with its suspected ocean beneath a frozen surface, remains the most promising candidate. Astrobiologists believe that if life exists there, it will be microbial, possibly thriving in environments similar to Earth's deep-sea hydrothermal vents. These vents, where life survives without sunlight, show that life can persist in some of the most extreme environments, providing a template for what might exist beneath Europa's ice. The discovery of life in such a place would forever alter our perception of biology, proving that life can emerge in conditions radically different from those on Earth. Future missions will play a critical role in answering this question. NASA's LEC Europa-Clippertat mission, slated for launch in the 2020s, will explore Europa in unprecedented detail. Using a suite of scientific instruments, Europa Clipperter will fly close to the Moon's surface, scanning its icy crust, looking for evidence of subsurface water, and searching for signs of life. If Europa's ocean is indeed in contact with its rocky mantle, hydrothermal activity could provide the energy needed to sustain life, creating a tantalizing possibility that we are on the brink of discovering extraterrestrial biology within our own solar system. Ganymede, the largest moon in the solar system, also holds potential. While its surface appears less dynamic than Europa's, scientists suspect that a subsurface ocean exists beneath its icy shell. Ganymede's unique feature, a magnetic field, sets it apart from other moons and may play a role in protecting any potential life forms from harmful cosmic radiation. Exploring Ganymede could provide further clues about the habitability of icy worlds, particularly those with magnetic protection and subsurface oceans. Callisto, while geologically less active, offers a fascinating study of a more ancient and stable world. Its heavily cratered surface has remained largely unchanged for billions of years, preserving a record of the early solar system's violent past. Callisto's relative distance from Jupiter's intense radiation also makes it a candidate for future human exploration. If we are ever to establish a human presence in the outer solar system, Callisto could serve as a safe outpost from which to study the Jovian system more closely. Its stable environment, far from the intense radiation belts that surround the inner moons, would make it an ideal location for future missions aimed at understanding the outer planets. These moons also teach us about the varied environments that might exist on exoplanets orbiting distant stars. Many exoplanets discovered so far are gas giants like Jupiter, and some may have moons orbiting them, much like those in our solar system. By studying the moons of Jupiter, we can begin to understand how moons might influence habitability in other planetary systems, opening the door to the possibility of life on exomoons orbiting gas giants light years away. Jupiter's magnetosphere, another point of interest, is a colossal force of nature. Stretching millions of kilometers into space, it forms an invisible shield around the planet, trapping charged particles and creating intense radiation belts. These radiation belts pose significant challenges for future missions, both robotic and human, as the levels of radiation around Jupiter are far higher than anywhere else in the solar system apart from the Sun. Yet, despite these challenges, the magnetosphere provides valuable insight into the behavior of planetary magnetic fields and their interactions with the solar wind. Understanding these dynamics not only informs us about Jupiter but also about other planets and even stars, as magnetic fields are fundamental to understanding how celestial bodies interact with their environments. One of the more unexpected and visually stunning phenomena associated with Jupiter's magnetosphere is its auroras. Much like the northern and southern lights on Earth, Jupiter experiences auroras at its poles, caused by the interaction between the planet's magnetic field and charged particles from the Sun. However, Jupiter's auroras are far more powerful, glowing with a brightness and intensity that dwarfs Earth's auroral displays. These brilliant light shows are not just beautiful but also scientifically significant, offering a glimpse into the powerful forces at work within the planet's magnetic field. As we look to the future of space exploration, Jupiter remains a central focus. New missions to the Jovian system will continue to push the boundaries of what we know about gas giants, their moons, and the potential for life beyond Earth. Missions like JUSTA Jupiter Icy Moons Explorer, planned by the European Space Agency, will study Ganymede, Callisto, and Europa in greater detail, investigating their potential habitability and providing new insights into the processes that shape these icy worlds. In many ways, the study of Jupiter is a reflection of humanity's broader quest for knowledge. It represents the natural curiosity that drives us to explore the unknown, to seek answers to fundamental questions about the universe and our place within it. As we continue to unlock the secrets of Jupiter and its moons, we are reminded that the cosmos is vast, filled with mysteries waiting to be discovered. Jupiter, with all its grandeur and complexity, serves as a reminder of both the power of nature and the endless possibilities that await us as we continue to explore the universe. In the end, Jupiter is not just a planet, it is a symbol of exploration, a cosmic laboratory that challenges our understanding of everything from planetary formation to the potential for life in the most unexpected places. Its swirling storms, towering magnetic field, and icy moons inspire wonder and curiosity, drawing us ever closer to the answers that have eluded humanity for millennia. The more we learn about Jupiter, the more we realize how much there is yet to discover, not only about this distant giant, but about the universe as a whole. And as we continue our journey of exploration, Jupiter will remain a guiding star, illuminating the path toward greater understanding and discovery. As we continue our exploration of Jupiter, the planet's mysteries deepen, reminding us that the more we learn, the more there is to uncover. Jupiter stands as a testament to the scale and complexity of the universe, a dynamic world that both challenges our scientific understanding and ignites our curiosity about what lies beyond. Its vastness, from the swirling clouds of its atmosphere to the icy depths of its moons, offers a window into the formative processes that shape not only our solar system, but planetary systems across the cosmos. One of the key aspects of Jupiter's study is its role in the early development of our solar system. Scientists theorize that Jupiter was one of the first planets to form, coalescing from the gas and dust of the primordial solar nebula. Its massive size allowed it to dominate its region of space, and it likely played a critical role in shaping the orbits of other planets. As Jupiter gathered material, its gravity influenced the movement of smaller bodies, either ejecting them from the solar system entirely or pulling them into stable orbits. This early gravitational influence may have prevented the formation of a second planet in the asteroid belt, leaving that region populated by smaller, rocky objects. The study of Jupiter's formation also informs our understanding of how other gas giants form in distant planetary systems. As we discover more exoplanets, particularly those similar to Jupiter, we can compare these distant worlds to our own gas giant. Many of the exoplanets discovered in recent years, particularly the so-called hot Jupiters, orbit much closer to their stars than Jupiter does to the Sun. By studying Jupiter, scientists are refining their models of planetary formation and migration, helping to explain why some gas giants remain in stable, distant orbits while others migrate closer to their parent stars. Jupiter's influence extends beyond its own orbit. Its gravitational pull affects the entire solar system, including the asteroid belt and the Oort cloud, a distant region filled with icy bodies that orbit the Sun at great distances. Jupiter's gravity can capture comets and asteroids, pulling them into orbit around the planet or sending them hurtling toward the Sun or outer reaches of the solar system. This process, known as gravitational slingshotting, has played a significant role in shaping the trajectories of comets and other small bodies. Jupiter's powerful gravitational field also helps to shield the inner planets, including Earth, from potentially catastrophic impacts. By diverting or capturing comets and asteroids that might otherwise collide with the inner planets, Jupiter acts as a kind of cosmic protector. This protective role has earned Jupiter the nickname the Guardian of the Solar System, as it reduces the likelihood of life-threatening impacts on Earth. However, Jupiter's gravity is a double-edged sword. It can also send objects from the outer solar system toward Earth, contributing to the frequency of impacts over geological time. In fact, some of the most significant impacts on Earth's history, including the event that likely led to the extinction of the dinosaurs, may have been influenced by Jupiter's gravitational interactions. The exploration of Jupiter also brings us closer to understanding the potential for life beyond Earth. While Jupiter itself is unlikely to host life due to its extreme atmospheric conditions, its moons, especially Europa, are prime candidates for astrobiological study. Europa's subsurface ocean, hidden beneath a thick layer of ice, has long been considered one of the most promising places in the solar system to search for life. The tidal forces generated by Jupiter's gravity keep Europa's ocean in a liquid state, providing a potential habitat for microbial life. Similar to deep-sea hydrothermal vents on Earth, which teem with life despite being isolated from sunlight, Europa's ocean may harbor ecosystems fueled by chemical energy. NASA's Like Europa Clipper-type mission, set to launch in the coming years, will focus on investigating Europa's habitability. The spacecraft will perform multiple flybys of Europa, using advanced instruments to analyze the composition of its icy surface, study the thickness of the ice, and search for plumes of water vapor that might provide clues about the ocean below. If the mission detects signs of life or even the chemical precursors of life, it would revolutionize our understanding of biology and the potential for life in the universe. The discovery of life in Europa's ocean, even in its simplest microbial form, would suggest that life could arise in a wider range of environments than previously thought. Jupiter's other moons, including Ganymede and Callisto, also offer intriguing possibilities. Ganymede, the largest moon in the solar system, is unique in that it possesses its own magnetic field. This magnetic field, combined with the suspected presence of the subsurface ocean, makes Ganymede another candidate in the search for life. While the conditions on Ganymede are less extreme than on Europa, its vast size and complex geological history make it a fascinating target for future missions. Callisto, with its ancient, heavily cratered surface, offers a different kind of scientific opportunity. Unlike Europa and Ganymede, Callisto shows little evidence of internal geological activity, and its surface has remained largely unchanged for billions of years. This makes Callisto an ideal location for studying the early history of the solar system, as its surface preserves a record of ancient impacts and processes. Callisto's relatively low levels of radiation compared to the other moons of Jupiter also make it a potential location for future human exploration. If humans ever venture beyond the inner solar system, Callisto could serve as a base for missions to study Jupiter and its moons in greater detail. Beyond its moons, Jupiter's rings, though faint and less spectacular than Saturn's, offer valuable clues about the planet's history. These rings are composed mainly of dust and small particles, likely originating from impacts on Jupiter's moons. Studying these rings can help scientists understand the processes that govern ring formation and evolution, not just around Jupiter but also around other planets with ring systems including Saturn, Uranus, and Neptune. Rings can serve as indicators of a planet's gravitational influence and its interactions with nearby objects, offering insights into the dynamics of planetary systems. As we continue to study Jupiter, we are reminded of the interconnectedness of the solar system. Jupiter's gravity, magnetosphere, and dynamic interactions with its moons influence the behavior of objects across vast distances, shaping the environment around it in ways both subtle and profound. The study of Jupiter is not just the study of a distant planet. It is the study of the forces that shape planetary systems and, by extension, the universe itself. Looking ahead, the future of Jupiter exploration promises even more exciting discoveries. Missions like JUICE Europa, Clipper, and potential future human missions to the Jovian system will bring us closer to understanding the mysteries of this giant planet and its complex system of moons. Each new mission builds on the discoveries of the past, expanding our knowledge and pushing the boundaries of what we know about the universe. Jupiter, with all its grandeur and complexity, stands as a beacon of exploration. It is a reminder of the vastness of the cosmos and the boundless potential for discovery that lies ahead. As we continue to unlock the secrets of this gas giant, we move closer to answering some of the most fundamental questions about our origins, the nature of life, and the forces that govern the universe. Jupiter, in all its swirling clouds and dynamic moons, serves as both a challenge and an inspiration, guiding humanity's journey of exploration towards ever greater horizons. As we continue to peer into the mysteries of Jupiter, its intricate dynamics and profound influence on the solar system invite us to explore even deeper into the origins and future of planetary science. Every mission, from the earliest telescopic observations to the cutting-edge technology of modern spacecraft, has revealed a planet that is not only majestic in scale, but deeply interconnected with the history and evolution of our entire solar system. Jupiter, in many ways, is a keystone planet. By studying it, we unlock answers to questions that reach far beyond its gaseous atmosphere. One of the critical areas of research that Jupiter inspires is our understanding of planetary atmospheres and weather systems. The planet's atmosphere is a massive chaotic storm of gases with bands of swirling clouds driven by powerful jet streams. The most iconic feature of this atmosphere, the Great Red Spot, is a massive anticyclonic storm that has raged for centuries. While it is shrinking, the Great Red Spot remains large enough to engulf the Earth. Scientists are still unraveling the mysteries of this storm, what powers it, what sustains it, and why it has persisted for so long. Jupiter's other weather phenomena are just as fascinating. The planet experiences smaller but equally intense storms scattered across its atmosphere. The planet's rapid rotation, the fastest of all the planets, completing a day in just under 10 hours, helps to drive these powerful systems. This rapid spin creates strong winds and fierce turbulence, causing the bands of clouds to appear distinct. Each of these bands represents a different layer of Jupiter's complex atmosphere, with varying temperatures, pressures, and compositions. The dynamics of these weather systems provide scientists with valuable data to refine our understanding of atmospheric science, both on Earth and on other planets. Beneath Jupiter's thick atmosphere lies a layer of metallic hydrogen, a state of matter that doesn't exist naturally on Earth. At the extreme pressures found inside Jupiter, hydrogen atoms are squeezed so tightly together that their electrons move freely, making the hydrogen act like a metal. This metallic hydrogen is believed to generate Jupiter's immense magnetic field. which is the strongest of any planet in the solar system. The behavior of metallic hydrogen inside Jupiter is still poorly understood, but it provides a unique opportunity to study matter under extreme conditions, potentially offering insights into the interiors of other gas giants and even stars. Jupiter's magnetic field extends far into space, creating a magnetosphere that is enormous by any standard. It is so large that it could contain all of the other planets in the solar system combined. This magnetosphere traps charged particles from the solar wind, creating powerful radiation belts that can be hazardous to spacecraft and any future missions to the planet's moons. The interaction between Jupiter's magnetosphere and its moons is a subject of ongoing study. The moons of Jupiter, particularly Io, play a significant role in shaping the dynamics of this magnetic field. Io's volcanic activity, driven by tidal forces from Jupiter, spews vast amounts of sulfur dioxide into space. This material becomes ionized and forms a plasma torus that circles Jupiter, feeding the planet's magnetosphere and influencing its behavior. The study of Jupiter's magnetosphere also provides a valuable analog for understanding the behavior of other planets, particularly exoplanets. Many gas giants in distant star systems are exposed to intense stellar radiation, much like Jupiter's interaction with the solar wind. By studying how Jupiter's magnetic field protects its atmosphere and shapes its environment, we can draw parallels with these exoplanets, offering clues about their atmospheric composition, potential habitability, and overall stability. The moons of Jupiter, as diverse as they are, offer an extraordinary laboratory for exploring a wide range of geological and potentially biological processes. Each of the Galilean moons, Io, Europa, Ganymede, and Callisto, represents a unique world with its own history and characteristics. While Io is the most volcanically active body in the solar system, Europa, with its icy surface and subsurface ocean, holds the greatest promise for finding life beyond Earth. The potential for life in Europa's ocean has captured the imagination of astrobiologists around the world. The tidal forces that Jupiter exerts on its moons are powerful, particularly on Europa. These forces generate heat through friction as Europa is squeezed and stretched in its orbit around Jupiter. This internal heating likely keeps the ocean beneath Europa's icy surface in a liquid state, despite the extreme cold at the moon's surface. In recent years, observations from telescopes and spacecraft have detected water vapor plumes erupting from Europa's surface, further supporting the idea that its ocean may be in contact with the moon's rocky mantle, a condition that could foster life. The search for life on Europa is a central focus of upcoming missions, including NASA's LEG Europa Clippertat and the European Space Agency's LEG Ajustat mission. These missions will conduct detailed investigations of Europa's surface, studying its composition, structure, and potential for habitability. If life exists in Europa's ocean, it would likely be in microbial form, thriving in the dark, cold depths where chemical reactions of the ocean floor provide energy. The discovery of even the simplest forms of life would have profound implications for our understanding of biology and the potential for life elsewhere in the universe. Ganymede, the largest moon in the solar system, presents another intriguing environment. Its magnetic field, unique among moons, suggests that Ganymede's interior is more active than previously thought. Like Europa, Ganymede may also harbor a subsurface ocean, though it lies much deeper beneath the surface. The study of Ganymede could provide insights into the conditions necessary for magnetic field generation, as well as the potential for life in icy worlds far from the Sun. Callisto, with its heavily cratered surface, offers a window into the solar system's ancient past. Its surface, largely unchanged for billions of years, preserves a record of impacts and geological processes from the early days of the solar system. Callisto's distance from Jupiter's intense radiation also makes it a potential candidate for future human exploration. If humans ever venture into the outer solar system, Callisto could serve as a base for scientific missions, allowing for safe study of Jupiter and its moons while avoiding the hazards of the planet's radiation belts. As our understanding of Jupiter and its moons deepens, the planet remains a gateway to larger questions about planetary formation, the dynamics of giant planets, and the potential for life elsewhere in the universe. Each new mission adds a piece to the puzzle, revealing new mysteries and challenging our assumptions about what is possible in the cosmos. Jupiter's influence extends far beyond its immediate surroundings. Its gravitational pull continues to shape the orbits of asteroids, comets, and even other planets. Its role as the guardian of the inner solar system, protecting Earth from frequent impacts, highlights the interconnectedness of the solar system and the delicate balance required for life to thrive. As we look to the future, the exploration of Jupiter promises to be one of the most exciting frontiers of planetary science. With advanced spacecraft, powerful telescopes, and cutting-edge technology, humanity is poised to uncover the secrets of this gas giant and its complex system of moons. Each discovery will bring us closer to understanding not only Jupiter but the broader forces that govern the evolution of planets and the potential for life in the universe. In this grand narrative of cosmic exploration, Jupiter stands as a symbol of the endless curiosity that drives us to explore the unknown. It reminds us that, while we have learned much about our solar system, there is still so much left to discover. Jupiter's vastness, its swirling storms, and its dynamic moons offer an invitation to journey deeper into the cosmos, to push the boundaries of what we know, and to embrace the mysteries that lie beyond the stars. Jupiter, the colossal giant of our solar system, represents far more than just a planet. It is a gateway to understanding the intricate workings of planetary systems, the dynamics of gas giants, and the potential for life beyond Earth. As we continue to explore its turbulent atmosphere, powerful magnetic field, and fascinating moons, we are not just unraveling the secrets of a distant world, we are deepening our understanding of the universe and our place within it. From the swirling storms of the Great Red Spot to the icy oceans of Europa, every aspect of Jupiter invites further discovery. Its gravitational influence, its role as a protector of the inner planets, and its intricate interactions with its moons paint a picture of a planetary system both ancient and active, dynamic and mysterious. Missions like Io Europa, Clipper, and JUICE will undoubtedly continue to reveal new layers of complexity, expanding our knowledge of planetary science and the potential for extraterrestrial life. In the broader scope of space exploration, Jupiter serves as a reminder of the boundless opportunities that lie beyond our home planet. Each new discovery challenges us to think bigger, to question more deeply, and to push the limits of what is possible in science and exploration. Jupiter is not just a planet in the night sky, it is a symbol of the human spirit's relentless curiosity and desire to explore the unknown. As we continue to reach out into the cosmos, Jupiter will remain a guiding light, leading us toward new frontiers and inspiring the next generation of explorers and scientists to dream even bigger. The story of Jupiter is far from over. It is in many ways just beginning. As technology advances and our ability to explore the outer solar system grows, Jupiter and its moons will continue to play a pivotal role in the next great chapter of space exploration. And in that journey, we may not only uncover the secrets of the distant gas giant, but also find answers to some of the most profound questions humanity has ever asked. Where did we come from? Are we alone in the universe? And what lies beyond the horizon of our understanding?